Here's a trap I watch people fall into constantly. They decide to learn Python properly before touching machine learning, so they start a Python course. 40 hours in, they're deep into file handling, decorators, and object-oriented design patterns they will never once use in a data science job, and machine learning is still nowhere in sight. That's not learning. That's productive feeling procrastination. We're not doing that. Today you get the 20% of Python that machine learning actually uses, and then we go straight back to building things. No detours into territory you don't need yet, and if a tutorial ever tells you to learn classes and decorators before you've trained a single model, close it and come back here. 12 concepts, taught as drills rather than lecture, because reading my code and writing your own use different muscles, and today we are building the second one. By the end you'll write, unaided, the exact function that's this course's official finish line test for Python. Let's go. A variable is a labeled box holding a value, nothing more mysterious than that. Python figures out what kind of value is inside for you. You never declare it up front the way some languages force you to. 4 kinds show up constantly. A string, text always in quotes. An integer, a whole number. A float, a number with a decimal point. And a boolean, which is only ever true or false. Name a box, put a value in it, and Python remembers both the value and its type for as long as that box exists. Strings carry built-in tools called methods for the transformations you'll do constantly. Strip removes whitespace from both ends, useful because real-world text is full of stray spaces nobody notices until code breaks on them. Upper and title change case, and the one you'll type more than any other. The F string, which lets you drop a variable straight into a sentence by putting an F before the opening quote and wrapping the variable name in curly braces. Instead of gluing text and variables together by hand, you just write the sentence with the values sitting inside it. A list is an ordered, changeable collection written in square brackets. Append adds an item to the end. Len tells you how many items are inside. That part's intuitive. The part that trips everyone up is this. Positions count from 0, not 1. Here's why, properly, not just that's the rule. An index isn't really a position number, it's an offset, a distance traveled from the start of the list. The first item sits exactly where the list begins, 0 steps in, so it's item 0. The second item is 1 step further along, so it's item 1. You're not counting items, you're measuring distance from the front. Once you see it that way, it stops being an arbitrary programmer quirk and starts being obvious. And it means the last useful index in a list of 5 items is 4, not 5. A classic source of a beginner error we're coming back to shortly. Dictionaries are, without exaggeration, the single most useful structure you'll use in data work. A list finds things by position, item 0, item 1. A dictionary finds things by name. You store pairs, a key and a value, and you look values up by their key rather than by remembering where you put them. Think of one row of real-world data, a single customer, a single student, a single patient. It isn't naturally a list, because item 0 tells you nothing. It's naturally a dictionary. Name maps to a name, score maps to a number, and so on. Square brackets with the key inside reads a value out. The same syntax with an equal sign updates it, or creates a brand new key if it wasn't there before. You'll represent real rows of data as dictionaries constantly from part 4 onward. And when we load a whole spreadsheet into pandas, what you're really looking at is thousands of these, stitched together into one table. This is how a program makes a decision, runs one block of code or another, depending on whether something is true or false. If checks a condition first, elif offers a second condition if the first one failed, else catches everything left over. Python checks them top to bottom and runs the first branch that matches, then stops. It doesn't keep checking after it's found its answer, which matters the moment you have more than one condition that could technically be true at once. A for loop runs a block of code once for every item in a collection. This is how you process 1,000 rows of data the same way you'd process one, not by dragging a spreadsheet formula down, not by copying and pasting, but by writing the action once and letting the loop repeat it. Start a running total before the loop. Add to it once per item inside the loop. And by the time the loop finishes, that total holds the answer for the entire collection. A list comprehension is a for loop that fits on one line. Same job, one line instead of four, and you'll see this exact shape everywhere in real machine learning code. So it's worth seeing both forms side by side, doing the exact same thing. The long way: start an empty list, loop over the numbers, square each one, append it to the list, 4 lines to do one small job. The short way: square the number for every number in the list, all inside one set of square brackets. Read it out loud almost exactly as it's written, n squared, for every n in nums, and the syntax stops looking backwards. It's not a different idea. It's the same for loop, turned inside out and compressed. And once it clicks, you'll rarely write the long form again. A function packages up a block of code so you can reuse it with different inputs, and the honest reason you write one comes down to a single principle. You name a thing the moment you're going to do it more than once. The moment you catch yourself about to copy and paste a chunk of code with one small change, that's the function asking to be born. Def names it and lists its parameters, the inputs it expects. Return sends a value back out to whoever called it. Write it once, call it with a person's name today and a different name tomorrow, and the logic inside never has to be typed twice. That's the entire economic case for a function, less typing, and far fewer places for a bug to hide, because a fix inside the function fixes every single place that calls it. Rename greet to average later this video, and you'll see it's exactly the same shape, doing a more useful job. Import is how you pull in code someone else already wrote, tested, and improved, instead of writing everything from nothing. A library, sometimes called a module or a package, is just a bundle of functions somebody packaged up and shared. Math, the one built into Python itself, gives you square roots and constants like pi with one import line. NumPy, pandas, scikit-learn, all the heavyweight tools from part 4 onward work exactly the same way. One line, and years of somebody else's careful engineering becomes available to you, dot by dot. Now, a segment on its own, because this skill matters more than any single concept we've covered so far. Reading a traceback when your code breaks, calmly, without panic. Read it from the bottom up. The very last line is always the one that matters most, the errors class, then a colon, then the specific detail. The class tells you the category of mistake, and every error of a given class always means the same thing, no matter whose code you're reading, whether it's a 3-line script or somebody else's 10,000-line project. Above that, the file names and line numbers are the trail of exactly where it happened, oldest call first, top to bottom. For a short script, you barely need them. For a bigger program, that's exactly where you go look. Beginners panic at the wall of red text and read top to bottom, which is backwards. Bottom first, always. 4 errors, and if you learn what each class always means, you can debug code you've never seen before. Name error always means the same thing. You used a name Python has never heard of in this scope, nearly always a typo, or a cell run out of order, so the variable was never actually created. Type error always means the operation you tried isn't defined for the kind of value you gave it. Right idea, wrong kind of data, and the classic case is a number that arrived as text. Index error always means you asked a list, or a string, for a position that doesn't exist, which is exactly the zero counting trap from a few minutes ago, catching people out. And key error always means you asked a dictionary for a key it doesn't have, the dictionary's own cousin of index error, and just as easy to guard against once you know to check first. Right hands on keyboards. Open the Part 3 notebook. 12 numbered exercises, each with a tiny worked example first, and then a cell marked your code here. Actually type your own answer before looking at the solution. That's the entire point of a drills notebook. Exercise 1. 3 variables of your own, a string, an integer, and a boolean, printed alongside their types. Exactly the shape from the worked example a moment ago, just with your own values in the boxes. Exercise 2. Chains strip and title together on a messy string, then drops the result into an F string to build a clean sentence. 3 string tools in one line. 3 and 4, appending onto a list twice and printing its length, then indexing and slicing a 5-item list. First item, last item, and the middle three by counting positions from 0, exactly as we worked through it on the slide. 5. Adding a brand new key to a dictionary the same way you'd update an existing one. Square brackets, equals, done. 6 and 7. An if, elif, else deciding pass, borderline, or fail from a single mark. Then a for loop adding up a list of prices into a running total, rounded to 2 decimal places. 8. A list comprehension building word, lengths in one line, the compressed loop from the slide, now written by you. 9. Your own function, squaring a number, called once and printed, proof that def, one parameter, one return is a shape you can now produce from scratch. 10. Importing the random module and rolling a simulated die with one function call, the same import then dot pattern as math.sqrt, just a different library. 11. Combines two concepts at once. Loop over a dictionary of student scores with dot items, which hands you the key and the value together, and an if inside the loop printing only the students who scored 80 or above. That combination, loop plus condition over real data, is something you will do in literally every remaining part of this series. And 12, the finish line. Write a function called average that takes a list of numbers and returns their sum divided by their count. Test it on 10, 20, 30, and it should print 20. If you wrote that without peeking, you officially have enough Python for machine learning. Everything else you pick up as you go. Now the 4 broken cells, on purpose fixed live, in the exact order we met the errors on the slide. First, a misspelled variable favorite language typed with an extra letter, name error, and the fix is simply spelling it the way it was created. Second, adding 1 to a string that holds a number, type error, fixed by wrapping it in int first to actually convert it. The same fix you'll reach for constantly once real data arrives in part 4. Third, asking a 3-item list for position 5, index error, fixed by checking len first, and using a position that actually exists. And fourth, asking a dictionary for a key that was never added, key error, fixed with .get and a sensible default, so it returns unknown instead of crashing outright. Notice none of the fixes were clever. Read the class, know what it always means, fix the obvious thing. So what do you own now? 12 building blocks, variables, strings, lists, dictionaries, decisions, loops, comprehensions, functions, and imports, all of them things you typed yourself, not just watched. 4 error classes you can now name on site. And that one function, average, which is officially your proof that you're ready for part 4. Homework, and please actually do it. 1. Close this video and write the average function again, completely from memory, with nothing open beside it. 2. Break something on purpose in your own notebook, misspell a variable or index past the end of a list, and read the traceback out loud before you fix it. 3. Take the student scores exercise and extend it yourself. Print not just who passed, but the class average alongside it, using the average function you just wrote. The notebook's linked below, with full solutions to all 12 exercises at the bottom. Compare against those, don't just copy them. Part 4 is where the real project starts. 7,043 real customer records arrive. NumPy and pandas replace plain Python lists and dictionaries. And we find a column in that data that's been quietly lying to us about what kind of value it holds, which now you have exactly the vocabulary to understand. Subscribe so it finds you. And if you'd rather work through all of this as a structured course with graded exercises, the full guided path is on Udemy through CloudNimbus. Everything's linked below. You just wrote real Python from memory on purpose. I'm Rohan Singh, this has been CloudNimbus, and I'll see you in part 4.